Imagine for a moment that you are a chemist in the mid-19th century. You are working in a world where the very concept of a molecule is still being debated. You've discovered a substance called benzene. You know its elemental recipe: 6 carbon atoms and 6 hydrogen atoms. C6H6. On paper, this recipe is a nightmare. According to the rules of valence established at the time, carbon wants to form 4 bonds, and hydrogen wants to form 1. If you try to string 6 carbons in a line, you quickly realize you have way too many empty slots for only 6 hydrogens. To satisfy carbon's hunger for 4 bonds, you'd need a forest of triple bonds and double bonds, creating a molecule that, by all rights, should be incredibly unstable, explosive even. This mystery, the structure of benzene, would take nearly a century to fully solve, and the answer would eventually require us to rewrite the laws of how we think about electrons and reality itself. Today, we are going to dive deep into the architecture of benzene. We aren't just going to look at the hexagonal ring you see in textbooks. We are going to understand why it exists, the quantum mechanical glue that holds it together, and how its discovery changed chemistry forever. Let's start with the most intuitive way to think about a molecule, as a physical construction. If you have 6 carbons and 6 hydrogens, your first instinct might be a chain. But as we just noted, a chain of 6 carbons with only 6 hydrogens forces you into a high-energy, unstable geometry. In 1865, the chemist Auguste Kekulé famously claimed to have had a daydream. He saw a snake biting its own tail. This vision led him to a radical proposition. What if the 6 carbons aren't in a line, but in a ring? Picture this: a perfect hexagon of carbon atoms. To satisfy the 4-bond rule for each carbon, Kekulé suggested that the ring had alternating single and double bonds. Each carbon is bonded to one hydrogen, one neighbor by a single bond, and its other neighbor by a double bond. 1, 2, 1, 2, all the way around the circle. In 1865, the chemist Auguste Kekulé famously claimed to have had a daydream. He saw a snake biting its own tail. This vision led him to a radical proposition. What if the 6 carbons aren't in a line, but in a ring? Picture this: a perfect hexagon of carbon atoms. To satisfy the 4-bond rule for each carbon, Kekulé suggested that the ring had alternating single and double bonds. Each carbon is bonded to one hydrogen, one neighbor by a single bond, and its other neighbor by a double bond. 1, 2, 1, 2, all the way around the circle. In the world of chemistry, a double bond is shorter and stronger than a single bond. If Kekulé was right, benzene shouldn't be a perfect hexagon. It should be a pulsing, or lopsided hexagon, with 3 short sides and 3 long sides. However, when chemists finally gained the tools to measure the distances between atoms, they found something shocking. Every single bond in the benzene ring is exactly the same length, not an average over time, but physically identical. At 1.39 angstroms, these bonds are shorter than a standard single bond, 1.54, but longer than a standard double bond, 1.34. It's as if the bonds are 1.5 bonds. Kekulé tried to fix this by suggesting that the double bonds were oscillating, flipping back and forth so fast that we just see an average. But as we'll see, the truth is far stranger and more beautiful than a simple flip-flop. To understand what's actually happening, we have to look past the sticks and balls of 19th century models and look at the electrons. Let's build the benzene molecule from the ground up, using our modern understanding of orbitals. First, look at a single carbon atom in the ring. Carbon has 4 valence electrons. In benzene, each carbon decides to hybridize its orbitals. It takes its 2s orbital and 2 of its 2p orbitals and mixes them together to create 3 sp2 hybrid orbitals. Visualize these 3 orbitals as flat petals on a flower, spaced exactly 120 degrees apart in a single plane. These petals form the backbone of the molecule. One petal points to a hydrogen atom, and the other 2 point to the neighboring carbon atoms. These head-on overlaps are called sigma bonds. They are the strong, rigid frame of the hexagon. But wait. Carbon had 4 valence electrons. We've only used 3. The 4th electron lives in a p orbital that didn't get hybridized. This orbital looks like a dumbbell, standing vertically, perpendicular to the flat plane of the ring. Now, picture the whole ring. You have 6 carbon atoms in a flat circle. Each one has a vertical dumbbell-shaped p orbital sticking up and down. In a normal double bond, 2 of these dumbbells would lean toward each other and overlap, But in benzene, every p orbital is perfectly spaced to overlap with the neighbors on both star sides. Instead of 3 separate double bonds, the 6 p orbitals merge into 2 continuous donut-shaped clouds of electron density, one above the plane of the ring and one below. This is the aha moment. The electrons aren't living between specific pairs of atoms. They are delocalized. They are free to roam around the entire 6-carbon circuit like cars on a circular racetrack. This is why all the bonds are the same length. They aren't alternating single and double. They are all part of one unified cyclic electronic system. This concept is called resonance, and it's often one of the most misunderstood concepts in chemistry. Let's clear up a common misconception. When you see 2 different Kekulé structures drawn with an arrow between them, it does star, not star, mean the molecule is vibrating between those 2 states. Think of it this way. Imagine a biologist discovers a new animal. To describe it to a friend, they say, it's like a cross between a unicorn and a dragon. Does that mean the animal is a unicorn for half the day and a dragon for the other half? No. It's a stable, third thing that simply has characteristics of both, but we lack a single familiar word to describe it. Benzene isn't switching between structures. Its star is star, the hybrid. It is a resonance hybrid. This delocalization of electrons provides a massive boost in stability, something we call resonance energy. How do we know this isn't just a pretty theory? We can prove it with thermodynamics, the study of energy. Let's look at a process called hydrogenation, adding hydrogen to a molecule to break its double bonds. We can measure exactly how much heat is released when we do this. First, let's take cyclohexene, a 6-carbon ring with just one double bond. When we hydrogenate it, it releases 120 kilojoules of energy per mole. Now let's look at a ring with 2 double bonds, 13 cyclohexadiene. Logic suggests it should release twice as much energy, right? And it does, roughly 232 kilojoules. By this logic, benzene, which Kekulé thought had 3 double bonds, should release 3 times the energy of the single bond version. We expect 360 kilojoules. But when we actually run the experiment on benzene, the result is only 208 kilojoules. The answer is a resounding no. In fact, some rings are actually star-unstable star because of their geometry. This brings us to Huckel's rule and the concept of aromaticity. For a molecule to be aromatic, meaning it shares that special benzene-like stability, it has to meet 4 strict criteria. First, it must be cyclic. Second, it must be planar. Third, it must be fully conjugated. And fourth, the most mathematical rule, it must have 4n plus 2 pi electrons, where n is any whole number, 0, 1, 2, 3. Let's do the math for benzene. It has 6 pi electrons. If we set 4n plus 2 equal to 6, we find that n equals 1. Since 1 is a whole number, benzene is aromatic. Why does 4n plus 2 matter? This is where we reach the deepest level of the dive, molecular orbital theory, and the Frost circle. Imagine a circle. Now imagine drawing the shape of your molecule inside that circle, with one vertex pointing straight down. For benzene, we draw a hexagon inside the circle, point down. Every place where the hexagon touches the circle represents an energy level for the electrons. In benzene's hexagon, you'd have 1 level at the very bottom, then 2 levels slightly higher up, then 2 more higher still, and 1 at the very top. Now we fill these levels with our 6 electrons, starting from the bottom. Each level can hold 2 electrons. The first 2 go into the lowest level. The next 4 fill the next 2 levels perfectly. Notice what happened. All the electrons are in bonding, orbitals, and they have completely filled every available low-energy slot. This is the electronic equivalent of a closed shell, like the noble gases. It's a state of perfect balance. If you tried this with the 4-carbon square of cyclobutadiene, you'd find you have 2 electrons, hanging out in half-filled orbitals, which is like having an unfinished construction project. It's restless and unstable. This closed shell magic is the secret sauce of aromaticity. It's what makes benzene the gold standard of organic architecture. So why does this matter to you? You might think benzene is just a specialized chemical in a lab, but its structure is a fundamental building block of the world around us. The journey to establish the structure of benzene is a microcosm of the history of science itself. We started with a mystery of simple counting, C6H6. We moved to a structural leap with Kekule's ring. We hit a wall when the physical measurements didn't match the simple models. And finally we had to look into the fuzzy world of quantum mechanics to see that electrons aren't just dots on a page, they are waves that can harmonize. When you see that simple hexagon with a circle in the middle, don't just see a shape, see a perfectly tuned electronic circuit. See the 152 kilojoules of energy holding it together. See the vertical p orbitals overlapping in a silent quantum dance. Benzene isn't just a molecule. It's a masterclass in how nature finds stability through symmetry and sharing. It reminds us that sometimes the parts aren't as important as the way they all hum together in unison.